Hello and welcome to our lab on Newton's laws of motion. Newton's first law says that in order for there to be an acceleration, there must be a force. Newton's second law sort of puts the relationship to that. It says F equals ma, or the force is related to the product of the mass and the acceleration of the system. The net force is equal to the system mass times the system acceleration. Newton's third law says that there are no forces in isolation. In order to push or to pull, you have to have an object to be the recipient of your push or your pull. And so these two objects that experience the same force but in opposite directions are called, oftentimes, a Newton's third law pair. And so when we draw a force on a force diagram, often we ask, now what is the Newton's third law pair of this force? And you would then try to figure out where's the other side of this equal and opposite reaction. Now here in front of me I have this apparatus, and this apparatus simply is called a modified Atwood machine. An Atwood machine is simply a pulley with a cord draped over it and two masses on each end of the cord. If those masses are equal, there will be no net force or no acceleration. However, if those masses are unequal, there will be a net force downward on this side, and the system will begin to rotate. This mass will go downward, that mass will go upward, and there will be an acceleration of those masses. Now the modified Atwood is simply this. Instead of the pulley having a cord downward on both sides, here's our pulley, and our cord is horizontal to this cart here. So one of the masses is on a low friction track. The other mass is dangling downward at the other end of this string. I can put a hanging mass here, and it will pull the cart down the track. And this is called the modified Atwood machine. Now here I have a diagram of a modified Atwood machine. You see the mass of the cart is M1, the hanging mass is M2. And so this system mass is a total M1 plus M2. That's the system mass. Now let's look at the forces that are involved here. And right now let's just interest ourselves with the forces on this cart. First of all, gravity pulls downward. There's a downward force with a magnitude of M1g. Now this gravitational force has its Newton's pair in the earth. The earth feels a force upward equal to M1g. This cart feels a force downward equal to M1g. That's a Newton's third law pair. But there's another force on this cart as well. The track itself is pushing upward on the cart. So the track is pushing up on a cart. That's called the normal force, or F sub n. Now the normal force here is equal to, like I said, the cart, the track pushing up on the cart. And so the second law pair of the normal force is, of course, the cart pushing down on the track. But we won't draw that force because we're only interested in forces acting on the cart. Now, because this cart is not accelerating upward or downward, we know that the net force vertically is 0. Therefore, the normal force here must be equal in magnitude to M1g, even though they're not a Newton's third law pair. Now this cart is in fact accelerating down the track. What this means is there's a force this direction. And that force we'll call the force of tension. There's a force of tension in that string that's pulling this cart down the track. And so if we take a look at this mass here, there's also a force of tension upward that's equal to the force of tension on the other side of the pulley. We're assuming a frictionless massless pulley. So this force of tension is equal on both sides, and it can be thought of as sort of an internal force. Even though they look to be in different directions, the direction is changed by the pulley, so those forces sort of internally cancel each other out. It's like an internal stress. But downward here, let's draw another force, and this is M2g, the weight of that mass. Now, experimentally here, we're just going to try to use this modified Atwood machine to sort of examine the relationship between force, mass, and acceleration, and maybe even verify Newton's second law. When we look at that relationship, F equals ma, it has three variables: force, mass, and acceleration. Well, in order to determine the relationship between two different variables, you have to control the third one. In this experiment, I want to look at the relationship between force and acceleration. That means I have to control for the system mass. My system mass must never change. My system mass is equal to the mass of this string plus the mass of the cart itself. And to make it a little heavier, to slow things down, I've put a couple of heavy masses on here, a couple of 200 grams. And then this little stack of a 20, and a 10 gram mass. That's my total system mass. That can never change because I want to hold that constant while I vary the net force and the acceleration. Now, I can't just get the hanging weight from anywhere because that will be introducing more system mass. My hanging weight has to come from what I already have. So let me start with this 10 gram mass. I'll put it onto this end, and now I have suddenly a net force on the cart. However, my total system mass has not changed. Now I have two ways that I can measure the acceleration of this cart when it's released. First of all, using this motion sensor on the end, I can do it in the conventional way that we've done before in our force and acceleration, our position, velocity, and acceleration lab. Also, I have this photo gate down here. This is a smart pulley. It has 10 spokes, and the computer knows that those 10 spokes make one revolution. So every time the photo gate is tripped 10 times, the computer knows that a distance of one circumference of the wheel has been traveled. There are instructions on how to set this up in LoggerPro for the correct calibration for a 10-spoke pulley with the string in the groove in order to get an accurate measurement of distance versus time so that we can determine our acceleration. So now I'll release this and the cart begins to accelerate down the track, if I can keep it on the groove. And so once that happens, I can measure this acceleration with either of my devices. This screen here is so that the motion sensor can see it a little better. Now that was a very slow acceleration, in fact not much at all. I can increase the acceleration by increasing the net force. But first of all, let me record that data. I've got a value for the net force. That's this mass times gravity. I have a value for the acceleration, one that I can determine from LoggerPro by looking at graphs of distance versus time or velocity versus time, the acceleration being the slope of the velocity versus time graph, using either of these sensors, the motion sensor or the smart pulley with a string in the groove. And so that's a data point. I've got a net force and an acceleration. Now let me reset. In order to determine a graphical relationship between net force and acceleration, I need more than one data point. So let's put this 10 gram mass back down, and I'll take a 20 gram mass out. And now you see I have a greater net force. I've doubled my net force. However, the system mass has remained the same. I'm still controlling for that variable. And so now I get a greater acceleration of the cart down the track. And there's another data point. Another value of net force, another value of acceleration. Now because I have two 20s here and a 10, I can get different values of net force while keeping the system mass constant. I can have 10 grams times gravity, 20, 30, 40, and 50. Enough different values of net force to make a nice graph with those different values of associated acceleration. And now I can look at the graphical relationship between force and acceleration. It should be a linear relationship. F equals ma is in the form y equals mx, where the slope is a constant, in this case, the mass that we held constant. So from the slope of the graph, you should be able to determine the total mass of this cart if Newton's second law holds true. So one way to verify that then is to check the mass of the cart and compare it to the slope of your graph, which determines the relationship between applied force, the net force, and the system acceleration. The slope of that graph should be the system mass.